Welcome to The Explainer. Today we're diving straight into the rigorous science behind two radically different molecules that are tackling some of the absolute hardest problems in psychiatry: intractable addiction and profound despair. Both of these agents are operating right at the absolute frontier of neuroscience. But as we're going to see, they get there using completely different pharmacological tools, totally different treatment models, and wildly different risk profiles. I love this quote because it brilliantly captures the core of our exploration today, reaching the same frontier, addiction and despair, by a route and a syringe at very different costs. It's a fascinating study in contrasts that's going to really challenge how we think about healing the brain. So here's our roadmap for today. First, two drugs, two frontiers. Next, Ibogaine, the broad reset. Then ketamine, the glutamate lever. After that, the shape of treatment. Then we'll look at safety, opposite hazard curves. And finally, which one, for whom. All right, let's jump straight into section 1. Two drugs, two frontiers. Their origins literally could not be more different. It's actually kind of wild that a shrub root and an emergency room synthetic are treating the exact same frontier. On one hand, we have Ibogaine. It's this complex indole alkaloid extracted right from the root bark of the Tabernanthe iboga shrub in West Africa, where it was historically used to interrupt opioid withdrawal. Then, on the other hand, we have ketamine. This is a totally synthetic dissociative anesthetic. It was born in a laboratory back in 1962 for use on battlefields and is now evolved into a rapid intervention for treatment-resistant depression and acute suicidality. Moving on to section 2, Ibogaine, the broad reset. So when we look at Ibogaine's neuropharmacology, it acts less like a precision sniper rifle and way more like a broad-spread shotgun. It doesn't just hit one receptor, it hits multiple systems simultaneously. We're talking about a non-competitive NMDA receptor antagonist, a kappa and mu opioid modulator, a sigma-2 site ligand, a serotonin transporter inhibitor, and a nicotinic acetylcholine antagonist. Wow, right? Basically, there's no single receptor that explains what it does. Instead, its anti-addiction capability emerges from this incredibly broad polypharmacological combo that touches the opioid, glutamate, serotonin, and cholinergic systems all at exactly the same time. Now, you might be wondering, how does this broad activity actually translate to long-term change? Well, Ibogaine induces something called GDNF. That stands for glial cell line-derived neurotropic factor. In preclinical models, researchers found that microinjecting Ibogaine into the ventral tegmental area, which is a huge hub in the brain's reward circuitry, actually raised GDNF levels and drastically reduced drug self-administration in animals. And get this, blocking GDNF actually got rid of this therapeutic effect entirely. For a patient, this means GDNF is literally resetting the brain's reward circuits through a self-amplifying neuroplasticity loop. It's essentially breaking the physical chains of addiction. And this mechanism brilliantly illustrates exactly why Ibogaine's effects last for days. The liver enzyme CYP2D6 rapidly converts the parent drug into an active metabolite called noribogaine. So while Ibogaine itself only sticks around for a few hours, noribogaine has a massive plasma half-life, estimated at roughly 28 to 49 hours. It just keeps acting as a serotonin reuptake inhibitor and a kappa opioid ligand long after that initial intense experience is over. This creates a remarkably prolonged physiological tail. Let's shift gears to section 3, ketamine, the glutamate lever. Let's walk through this highly targeted, elegant 4-step cascade. We call this the disinhibition model. First, ketamine preferentially silences NMDA receptors on inhibitory interneurons. Essentially, it takes the brake off excitatory neurons. This causes a brief, rapid surge of glutamate in the prefrontal cortex. That surge then activates a second receptor called AMPA, which sets off this whole chain reaction involving BDNF and mTOR that drives rapid synaptogenesis. Basically, the rapid growth of new dendritic spines and synapses. So it's this physical neuroplasticity, not just the dissociative high, that's doing the actual therapeutic heavy lifting here. Now, I do need to throw in a quick, honest caveat here. These mechanistic models heavily rely on animal data, and they remain the leading scientific hypotheses, but they aren't the whole story just yet. Scientists are still actively debating the exact roles of specific enantiomers, like S-ketamine versus R-ketamine. Plus, there's an ongoing debate over a metabolite called HNK, which might actually produce antidepressant effects completely independently of that NMDA inhibition we just talked about. It's an incredibly rigorous and rapidly evolving field for sure. Moving right along to section 4, the shape of treatment. When it comes to the actual experience, Ibogaine demands one overwhelming single-session marathon. A therapeutic dose triggers a profound waking dream state lasting for hours, wrapped up in a total physiological experience that can take up to 36 hours. It's intense. But the payoff, as reported in observational series, is a steep, objective drop in opioid cravings and withdrawal symptoms in just 48 hours. Ketamine, on the other hand, it's a sprint. A standard research IV infusion takes maybe 40 minutes, and the severe weight of treatment-resistant depression can actually begin to lift in as little as 2 hours. I mean, the sheer speed of this relief is absolutely incredible. So, the really crucial takeaway here is the profound symmetry between these two treatments. Ibogaine asks for one grueling, massive session that leans on that long Ibogaine tail to create what looks like a durable, one-time reset. Ketamine provides incredibly fast relief, but, and this is a big but, because it's transient, a single dose typically fades within 1 to 2 weeks. That means it requires a repeating series of infusions and open-ended maintenance. Okay, let's look at Section 5, Safety, Opposite Hazard Curves.
When we talk about safety, Ibogaine's defining hazard is very acute, and it is cardiac. It directly blocks the hERG potassium channel in the heart. What this does is delay electrical repolarization and prolong what cardiologists call the QT interval. And this isn't just a theoretical concern. It actively raises the risk of a potentially fatal arrhythmia known as torsade de pointes. This is a severe, immediate physiological risk that demands a ton of clinical respect.
When we compare them directly like we're doing here, their hazard curves don't overlap at all. Ibogaine carries that acute cardiac risk, which means you absolutely need strict ECG screening and interventions, like the magnesium buffering they used in the recent Stanford Veterans study to protect the heart. Ketamine's risks, however, are totally different. They're chronic and behavioral. Heavy, sustained use causes documented bladder toxicity, specifically ulcerative cystitis, and it carries a very real abuse and dependence liability. So one threatens the heart acutely, while the other threatens the bladder and behavior chronically. Finally, that brings us to Section 6. Which one for whom? Right now, ketamine is an established legal medicine. It sits at Schedule 3, boasts an FDA-approved esketamine nasal spray, and has a massive base of randomized controlled trials backing it up. Ibogaine, on the other hand, remains a Schedule 1 controlled substance in the U.S., which has historically pushed patients to observational clinics in places like Mexico. But, that frontier is shifting rapidly. Colorado has initiated a first-of-its-kind state research pilot program, and Texas has actually committed a massive $50 million to state-funded clinical trials to finally build a rigorous evidence base for Ibogaine. I'm going to leave you with this question to ponder. As we've seen today, this really isn't a contest to crown a winner. It's a question of clinical fit. How is mainstream medicine going to adapt to embrace a one-time polypharmacological reset that requires intensive cardiac monitoring, right alongside a targeted glutamate lever that requires ongoing chronic maintenance? It is a truly fascinating challenge, as these two extraordinary molecules continue to reshape our deep understanding of neuroplasticity and healing. Thank you so much for joining me on this explainer, and keep questioning the science.